That was an unfortunate delay, but we'll try to make the most of the time that we have on hand. So my name is Amit Singh. I work as a senior solutions architect with EDB. My talk today is going to be a post-mortem of a production incident that we faced with a major bank. And through this incident, I would like to highlight how important is Commitlog for Postgres in general, and also highlight some concepts on how transaction IDs work and how they are tracked in Postgres. So yeah, that's the agenda. We first look at the evidence of a corruption. This is where we found the problem. We revisit some of the concepts of MVCC and understand how transaction IDs are tracked in Postgres. We collect some facts. This is basically after you are notified about an anomaly in a production database, you would typically go about understanding what's there in the system, what happened with the system in the past few days. And once we identify that, then we look at the exact corruption that we faced. And then we look at options to fix that corruption. Note that fixing corruptions are not always possible because they can be of various degrees of complexity. And at the end, we look at what are the lessons learned and a summary of the tools that we used to get through this corruption. Throughout the presentation, if you have any questions, feel free to raise your hand. Although we are short on time, I'll do my best to answer questions post the session. So yeah, this is where the problem starts. The customer has done a production, a major version upgrade from version 13 to 17. And post-upgrade, as most of you would be aware, that an analyze is needed to collect statistics. The customer here ran a vacuum, and they figured out that the vacuum is failing. The error here is this particular transaction ID. Postgres is not able to track the status of this transaction ID. And it's complaining that it's trying to look for a file in the PG_exact folder. This is something, so there are a few jargons here for folks who are new to Postgres, and that's why what I'll do next is I will revisit some of the concepts in Postgres and around MVCC, that's multi-version concurrency control. These are limited in nature to keep it specific to the issue at hand. So it's not an in-depth coverage of these concepts, but only the ones relevant to the corruption. So Postgres stores table data in files, and within a file, it stores data in chunks of 8 KB blocks. Most of you must be aware of it, so I'll rush through it, but at any point in time, if something is not clear, feel free to call it out. So yeah, this is typically how the blocks are organized in 8 KB chunks. And if you zoom into a particular block, you can see that there are certain header flags, and then there are line pointers which point to the actual tuples. Tuples are nothing but rows in Postgres. If you zoom within a particular tuple, which you can see here, you can see that a tuple has a lot of header information again before it actually stores the user data. So these headers are quite important and will be our topic of deep dive in this talk. Before we get to that, let me cover some more concepts. In Postgres, transaction IDs are tracked with two fields, xmin and xmax. So here, when I'm trying to insert a transaction, insert a row in this particular table, the transaction ID is 99, which is tracked in xmin, and xmax is basically for the transaction that actually updates or deletes this particular row. So here you can see that when you're trying to delete a particular row with the transaction ID 111, that gets tracked in the xmax field. These are two of the header fields for a particular tuple, but there are many more, and we will get to that in a bit. So far, we understand that xmin is the one responsible for inserting the data, and xmax is the one which is responsible for deleting or updating the data, or the tuple. So when you run an update, you can see that this particular transaction ID, xmin 99, had inserted the data, but now my transaction ID 100 is actually trying to update the data. So that the update in Postgres is executed as a delete plus insert. So 100 is the transaction ID that deleted this particular row, and a new version of that row got created with the same XID that is 100. And you can also see that now the line pointer is pointing to the new tuple. So the old one is now dead and the new one is live, assuming that this transaction goes ahead and commits itself in the future. And another thing to note here is these transaction IDs, whether they are committed or rolled back, is not tracked in the tuple so far. So the moment you run a commit, you may have run 10 different statements and might have affected millions of rows as part of those statements. When you run a commit, it's not practically possible for Postgres to go and update the status of the transaction as committed or rolled back in the tuple itself, because that would be it will consume a lot of time and will not be efficient. So the status of a transaction gets tracked into a separate structure, which I'll get to a bit later. A note about transaction IDs, they are 32-bit integers, and they are about 4 billion in total. So the way the transaction IDs work is, for example, if you look at 100 as the transaction ID of focus over here, the transaction IDs work in a circular buffer. So the roughly 2 million transactions in the past are what is visible to this particular transaction, and the other 2 billion of them are not visible because they are in the future. And Postgres needs to continue to free up these transaction IDs with a term called freezing. It needs to freeze the transaction so that these transaction IDs can be reused after we exhaust all the roughly 4.2 billion transactions. That's the circular buffer of transactions, that how Postgres manages transaction IDs. And coming to the question of what is Commitlog, because the main error that we got when we faced the corruption was that it could not access the status of a transaction. Commit logs are stored as by the folder name PG_exact. That's what you can see here within the data directory. And you can see various files in this directory which keep a track of whether a particular transaction committed or rolled back. So going back to the point, these transactions are not tracked in the row headers or the tuple headers. They are tracked in this particular structure. And why are these important? Because when you try to read a particular row as part of a select query or any kind of operation that you try to do, these transaction ID statuses are important to figure out whether you can actually see the row. If the tuple that is being read is still being modified in an in-progress transaction, a user is typically not allowed to see that data. Or if a particular tuple was actually inserted by a transaction which never committed, that's again something that's not supposed to be seen to other users. So yeah, that's why commit log is so much more important. It's the status of the commit of the transactions are stored in a buffer in memory. It's a small structure which allows for few transaction IDs to be tracked in memory, but there is also a structure on disk from where it is flushed from memory to the disk. And again, this structure on the disk is what makes sure that your transactions are durable, because when you run a checkpoint, these details are flushed onto the disk. When you do a shutdown, these transaction ID statuses are flushed onto the disk as well. And when the Postgres starts up, it also loads the data from the disk back into memory to make sure that it's able to make sense of whether a particular tuple is visible or not. Visibility of a particular tuple is governed by various complex visibility rules, and that's not the focus of this talk, but the status of a transaction is one of the important data that is needed to identify whether a tuple is visible or not. The removal of these commit log files, again, these commit log files are tracked based on the age of a particular transaction. So as you can see on this slide, there are 5 different databases, each of which have a minimum transaction ID which is known to be frozen. So when you do the minimum of all such databases available in your cluster, you come to know that this is particular point beyond which I don't need the commit logs to be tracked, and they can now be removed safely from the disk. So this procedure of removing the commit log files is governed by vacuum. When vacuum runs, and specifically when vacuum freezes certain transactions across the tables of your various databases that you have, that's where the minimum dat frozen XID, this horizon keeps moving forward, and that's how Postgres understands that there are certain amount of unnecessary clog files. The name clog used to be used before version 10 of Postgres. Post that, it was renamed to exact, PG_exact, but again, it's just a terminology thing that got changed from version 10 onwards. We'll also speak a bit about visibility map. So when a particular, so for example, if you see the 0th page over here, this has 3 tuples, and each of these tuples have two flags that are tracked by the visibility map. This visibility map is created the first time vacuum runs on your table. And the first field in this visibility map here says whether this tuple is supposed to be visible or not, and the second one tracks whether the particular tuple has been frozen or not. When I say frozen, it means that the xmin or the xmax are no more relevant, because Postgres now knows that this is a committed row, and the transaction ID for xmin or xmax has now been freed up for future use. So that's about the concepts that were related to this corruption. And now let's get to some facts. This database went through a major version upgrade from 13 to 17, as I already discussed. Post-upgrade, the vacuum analyze failed with that error message. We have already seen that message. Few things that we checked: there are no long-running queries. Historically, we have seen vacuum can be blocked for various reasons. 3 of the most common ones are: if you have a long-running query, it needs to hold a snapshot, and that can be a reason for blocking vacuum to do its cleanup job. If you have any prepared transactions which have not been committed, that can also be a reason. So uncommitted prepared transactions, none of that. No stale replication slots, which are also capable of holding back your vacuum. So these were just sanity checks. The table was 116 GB in size. The table, or this particular database, was last patched from 13.7 to 13.13 almost an year ago. And few more details. The table was an insert-only table used mostly to archive the event logs of customer accounts. Interestingly, no other table in this database was affected by this corruption. This was the only table. And when we traced back the database logs from 6 months ago, luckily the customer held database logs for up to 6 months. It's quite useful in production scenarios when you have history of your database logs as dated as 6 months or even more. That helped us identify that the corruption was present in the database even before the upgrade happened. So they were living with the corruption, never really impacted by the corruption, but it was just a silent ticking time bomb which had to be uncovered when they did the upgrade. You can see here that the age of the database, I've encapsulated or masked the name of the DB as to hide the facts about the actual database name or the table. So the age is roughly 1.1 billion. If you remember, I spoke about the 2 billion limit after which the freezing needs to kick in to reuse or free up the transaction IDs. So at 1.1 billion, they were almost 50% of the way through for a wraparound, after which Postgres would forcibly freeze all the transactions and the customer would face a downtime. So they were 50% through to that red zone, and that's when we started our troubleshooting on this scenario. Just keeping track of time since we already were delayed. So yeah, this brings us to the problem statement. Why were the commit logs removed? And the database still needed them while the commit logs were removed. And it's not normal. Getting to AM check. AM check is an extension that helps us scan tables and find anomalies that of various kinds, right? So running an AM check on this corrupted table, again, the name is masked. We were able to identify that there were about 6.1 million rows that were affected by the same type of corruption. If you can see the message, it says that this particular xmin precedes the oldest valid transaction ID. So what this means is my database thinks that the oldest valid transaction ID in the database is roughly 727 million, whereas there are some rows which have an xmin of 364 million or so. And again, this is not normal. That's not what you expect when you know that the freezing counter for the database has moved to 727 million. You don't expect any transaction IDs still hanging around which are lower than that. So just capturing the data of this list of corrupted rows in a table and creating few views to make more sense out of that data, because just by looking at the block number and the offset within the block, it's very hard to take any action, especially if you're dealing with 6.1 million of them. PG surgery is an extension that allows you to literally operate on a particular relation or a block within a relation. And by design, it can further corrupt your database. So it's something that can, basically the moment you start manipulating the tuple header flags by hand, which is not something that Postgres expects you to do, you are running the risk of making your indexes inconsistent. You can make your unique keys and foreign keys inconsistent, and you can actually end up crashing your database as well, because there is certain rules that govern what is visible and what is not. And when you try to bypass them, you are basically running a lot of risk. So this is something that should only be used as a last resort. It's only supposed to be used under the guidance of experts. Couple of functions that this extension allows you to do. It allows you to forcibly kill a particular row, which in our case, we know that certain rows had a transaction ID for which the status was not known. So we can forcibly choose to kill those rows, which means we are marking them dead, and vacuum can then eventually come and do the cleanup. It doesn't need to look at commit log for those rows, because we have marked the tuple header as killed. And we'll get to tuple headers in a bit to understand that how this is done. The second option is to freeze a particular tuple. Again, you can see that a tuple is, when you're trying to vacuum, there is a complaint of a particular xmin and on a particular block, that is block 0 and the third row within the block 0. And when you run the heap force freeze, you actually make sure that the tuple is live now without having to look at commit log. So again, here we have manipulated the tuple headers in a way to make the tuple visible, whereas in the previous one, we manipulated in a way that it made it dead. So you remember the dummy table and views that we created to track those 6.1 million rows which were corrupted. This is just an aggregate of that table, aggregate count of tuple headers from that corrupted table. A few functions that I would like to call out. Get the raw page. This is a function available from page inspect extension, again available in the contrib module of Postgres, so you don't need to install anything separately. The heap page items again looks at the same data and gives you a more readable version of the raw page. And heap tuple info mask flags is a function that allows you to read these two header flags of a tuple, and it gives you this information about what's stored or what's known to Postgres as part of the tuple header. The first field here, heap has null, has no significance to this corruption. It just means that this particular row has null values. It's just a tracker for Postgres. Heap has var width, means that it has fields like text column, which has a variable width, and you don't know, it's just there for the tracking. heap x max invalid means that there is no x max for this tuple yet. And if you look at the second one, again, it's the same one, heap x max invalid, with just an additional flag which says heap has external. This means that the tuple has data which has been toasted onto an external table called PGToast. For those who know, PGToast is a way for Postgres to handle data of variable length, which is practically not possible to fit within a particular 8 KB page. It chunks it and stores it into a separate table called PGToast, and there is one for each table. So the first two or the first three ones here are not relevant. The last one here, xmax invalid, is what is relevant to us. And even, so I grouped them in 3 different cases because these are the 3 different types of corruptions that we identified. The second one here has, so I'll ignore the first 3 here. Heap has null, heap has var width, and heap has external. These are not relevant to the corruption. Heap xmin committed means that we know that the xmin here has been committed. You remember I mentioned that Postgres doesn't track it when the transaction commits, but there are ways in which Postgres can keep a track of the transaction ID status in the tuple header subsequently after the transaction has committed or rolled back. So this field over here does exactly that. So heap xmin committed means that this xmin, the transaction who inserted this row, had committed successfully. That's known to Postgres already in the tuple header. And heap xmax invalid again means that nobody tried to update or delete this row so far yet. There's a third category which says heap xmin invalid and heap xmax invalid. This is quite interesting, and we'll get to. I did a bit of test to understand each of these headers, to understand what they mean exactly and in which scenarios would these combination of flags occur. So this is a test. I'm trying to insert 10 rows in a test table, and I'm also looking with the help of these extensions what the tuple headers look like. So initially when I insert the row, it says heap xmax invalid. It has no idea about whether the xmin committed or not. It only knows that xmax is not set. That's all I know. When I do a subsequent select on this table, Postgres actually is forced to look at Commitlog and see whether the xmin is committed or not. And when Postgres does that check on the Commitlog, it is also updating the tuple headers here. It says xmin committed, heap xmax stays as invalid. So this is just a demonstration of how a Commitlog is referred when Postgres needs to look for visibility of a particular tuple, and how that information is tracked in the tuple header. Eventually, when I run a vacuum freeze on the same table, you can see that we have xmin committed, but it also says xmin invalid. The reason it adds the xmin invalid flag is because now that tuple has been frozen, it also updates heap xmin frozen. So now when somebody comes to look at this tuple again, they don't need to look at the commit log again because they know that the xmin has been frozen and freed up. So this is one of the scenarios that we faced in the 3 scenarios that I talked about earlier. And there is a third scenario that we faced that was about a scenario where xmin and xmax were both invalid. What does that mean? So I tried to insert 10 rows again, and this time instead of committing, I did a rollback. Again, so again, the xmin here is supposed to be invalid because the transaction aborted or rolled back. So the xmax is invalid, that's what is known, but the moment I do a read on that, it says 0 rows because none of these rows are supposed to be visible, and the xmin invalid flag has been added now to the tuple header. So this shows that how another scenario on how an aborted transaction could affect the tuple header. So summarizing all of this information on one slide, which is where our recovery options also are. Heap xmax invalid, if you have this flag, it means that the transaction, like nobody has ever tried to validate the moment you try to read a particular tuple, Postgres has to go and validate the status of a transaction. That has never happened. That's all that this flag means. If you see heap xmin committed and heap xmax invalid, this means that nobody has updated this or deleted the transaction. And we also know that xmin has been successfully committed because somebody has in the past looked at this row through a select statement. And heap xmin invalid, heap xmax invalid is basically this row is known to be, the xmin is known to be aborted. And the reason it is known again is because somebody tried to look it up. The moment you try to look up a particular page, all the tuples within the page go through this visibility check. So if your tuple page, or rather a relation page has 10 rows, and you try to read a single row, it doesn't mean that Postgres will check the transaction ID status of that single row. It will do for all the tuples or the rows within that page. So with this, we had our options clear on how we can use the PG surgery extension to mark these rows as frozen, these rows as killed because we know that they were aborted, and we had no clue what to do with these because the transaction ID status of this particular set of rows, which were the maximum, these were about 4.1 million of them from the previous slide, where we had no clue about what happened to these rows in the past. And these things are dated so far in the past that there is no way for any tracking to help you with this. Luckily for the customer, it was an insert-only table which tracked only the event logs of when a particular customer account was accessed. And they had this transaction or this data streamed through Kafka to another system. So they didn't really need to do the recovery for these. They didn't really need to do the recovery for it, but in a critical system where these transactions could mean money or could mean critical details about a particular transaction, it would have been far more worse. But it just goes to highlight that how important is commit log, and if it can go missing from your database for some reason, what could be the potential impact. The probable RCA. One of the probable RCAs could be that someone went into the PG exact folder and manually deleted those files. It could be a DBA who's new to Postgres and didn't really understand the importance of it and had seen a space crunch on the server and thought I could clean up some data from here. Another probable RCA could be, and this is why we tracked the patching history of the server. The server was, for the longest period of time, known to be on 13.7, and after some time patched to 13.13. There was a bug fixed in version 13.8, which spoke about how visibility maps could, actually when vacuum tries to freeze a particular table, it does look at visibility map. That's the reason I brought up visibility map in the previous slide. That if a visibility map is telling vacuum that this page does not need to be looked, vacuum will simply skip that page. And that is probably what could have happened if the customer did not manhandle the data directory by hand. This is the possible RCA about why this corruption could have been caused, which again takes us to an important lesson that the minor version releases are there for a reason. They are bug fixes which do not change the behavior of your Postgres database. So the moment you have a minor version, please do not wait for it to become considered as a stable version. Minor version releases are meant to be applied as soon as they are available. So summarizing the lessons that we learned, do not try to modify or clean up any of these subdirectories within the PG data directory. These folders, again, I'm not talking about the configuration files because yes, you would modify the configuration files. I'm talking about the subdirectories like PG exact or PG subtrans, PG multi-exact, or any of those for that matter. These are supposed to be managed by Postgres processes and not to be handled by DBAs or anyone by hand. If the customer would have monitored the database age, they would have seen that this particular database of theirs the age of this database is growing at a rapid pace, is not keeping So there's a parameter by the name auto vacuum freeze max age, which tells Postgres that if a particular database, any table within a database has an age higher than this, it needs to be frozen. Basically, vacuum needs to freeze that particular table or the tuples within that table. And if your database age is growing beyond this number, it's supposed to send out an alarm. So please do that. I'm not going through all the best practices around what should be monitored. I'm only covering the ones which were relevant to this corruption. But yeah, it's very important that you have the right kind of monitoring. If the customer had monitoring on the database logs, those errors were reported way back. And the first time the error was reported was when the customer was supposed to really act on it, not really when the vacuum failed. So that brings us to an important point that errors in your database logs are there for a reason. They tell you a story. And it's easy for you to overlook some of the database logs because some of them could be user-created errors which are not relevant to your database health, but some of them could be really important. So yeah, that's about the database logs. Patch your database with the latest minor version as soon as they are available. Do not wait for a bug to really impact your production database. You wouldn't want to do that when the data is critical. And tools like AMCheck, CatCheck is a tool that is used to check corruptions in catalogs. And a dump and restore is also something that you can do on a regular basis. And these are just, just the way you would like to check your backups for their validity, whether they are successfully able to restore or not. You could also consider checking for corruptions in your database at a regular interval so that you're able to spot them and identify them way before they become too big to handle. So we had 6.1 million rows which were corrupted had the customer been a little more vigilant with their monitoring and checking for corruptions. They could have gotten away with a few hundred or few thousand corrupted rows rather than 6.1 million corrupted rows. A summary of the extensions that I used. Page inspect, it helps you to look at the raw tuple headers and the contents within a page, which will otherwise not be visible to a user. If you would have seen some of the queries returned 0 rows, but when you use page inspect, you actually look at all the rows, whether irrespective of whether they are visible or not, because you're looking at raw data. You're not looking at data that has been beautified for a user to consume. AMCheck to find the corrupted rows. PGCatCheck also does a similar job, but for catalog tables. PGSurgery was used to mark the rows killed or frozen. Again, use it with caution. Please use it under the guidance of an expert. PG visibility is again another one that we use to look at the visibility map flags for each of those corrupted tuples or the pages which had the corrupted tuples. Yeah, so that's a summary of all the tools and extensions that helped us. And in the end, I would like to give credit to InterDB. It's a site that I used to refer to some of the images that you saw for transaction ID tracking. And it's a very easygoing site to understand some of the internal Postgres concepts. A call out to the reviewers who helped me review the content on my slides. Just a courtesy thing on my end. And yes, with that I come to the end of my talk. For those who are interested, please visit the EDB booth. We have some open positions. You can scan the QR and look at open positions at EDB. And just a side note, I was hired at EDB through this same conference 7 years back. So if someone is looking for a change and is interested in doing interesting work with Postgres and AI, do consider the open positions at EDB. With that, I'll conclude my talk.